Everybody. So, as you may know, Monte Carlo path tracing is a rendering technique that is primarily used for offline video and image generation in the movie industry and medicine. The algorithm is iterative, meaning that the quality improves progressively with the growth of sample counts. The average of the samples forms a Monte Carlo estimate for every pixel. To address the problem of the excessive noise, some denoising can be applied to enhance the overall quality. However, even high-quality deep learning-based denoisers like optics or open denoisers often struggle to distinguish between fine details and the noise, resulting in excessive smoothing. This issue can be illustrated better in the visualization of the difference between the denoised images and the reference. Here, darker pixels indicate better results. Sometimes, especially in the scenes with a lot of fine details, denoising may even stop to improve the quality starting at some iteration. In such cases, the sequence of the denoised images even doesn't converge to the reference image. So it can be beneficial to actually blend the noisy Monte Carlo estimate with its denoised counterpart. The idea is to recover the fine details that can be missed during the denoising, meanwhile preserving the denoised areas where needed. Unfortunately, all the practical solutions proposed so far are deep learning based. It means that if the denoising algorithm changes, the model must be retrained. Moreover, these solutions require that the Monte Carlo estimate and its denoised counterpart to be obtained at the same iteration. That actually can be not efficient. We propose a solution that is free from these two limitations. So let's consider the following optimization problem. What we want to do is to blend noisy pixel n with its denoised counterpart d, so that the difference between the result and the reference image and the reference pixel r is as small as possible. Let's define the weight I of the noisy pixel n to be the number of iteration at which this noisy pixel was obtained. So we need to find a non-negative weight w for the denoised pixel. As the norm is not negative, the solution of this problem satisfies the following equation. On the other hand, the Monte Carlo estimate at the iteration k is the average of the samples obtained until the iteration k. And it is also true for the reference pixel because it's simply a Monte Carlo estimate obtained at some high sample number n. Let's substitute the first member of the sum by the definition of the Monte Carlo estimate. And then let's represent our denoised pixel value as the average of w different samples, which is actually the definition of the unbiased Monte Carlo estimate obtained at iteration w. Substituting the second member of the sum, you can actually see that the reference image, the reference value becomes the unbiased Monte Carlo estimate obtained at iteration I plus w. What does it mean? It means that instead of solving the initial problem, we can actually solve a simpler problem. And moreover, we can show that for the solution of this problem, the following equation is true. In other words, mean square error between the reference and the denoised pixel obtained at iteration I should be equal to mean square error between the reference and the noisy pixel obtained at iteration w. With this in mind, let's consider the convergence curves obtained for different scenes generated with Denisova framework. As you can see, all these curves can be approximated by lines in logarithmic scale. Moreover, if we know the convergence curve and we know the mean variance of the Monte Carlo estimate, we can easily obtain the number of iterations at which this Monte Carlo estimate was obtained. So, to solve our problem, we need to know just two things: the convergence curve, and we need to estimate the denoised image. To do the first, we can just apply a least square regression to the variance of the samples. And to obtain the second, we can apply Stein unbiased risk estimator to obtain the estimator of mean square error of the denoised image. To make it work, two conditions should be satisfied. First, samples should follow a normal distribution, and second, denoising function should be at least weakly differentiable. However, the convergence curve of the individual pixel is a little bit different from the convergence curve of the convergence curve of the entire image, and the difference can be explained by the presence of the outliers. On the other hand, and you can see this from the formula for sure, the values of sure can be negative, which has no physical sense. So we propose to apply a Gaussian blur for the estimations, and also to zero or to put to the magnitude values the negative values of sure. And the reasoning about this and all the details you can find in the paper. So we applied our method on the pre-generated scenes with the Denisova framework, and here you can see the crops of the landscape in the San Miguel scene obtained with open denoiser and optics. Blended is our result, and the error, as you can see, is lower for the both cases. The same regards the mean square error of the entire scene. We also measured the flip score for the scenes. Flip is the score that reflects the human perception and actually evaluates the visual quality of the images with respect to the reference. Also here, as you can see, our method produces better results. We also compared our method with the recently proposed deep learning-based method, PD, which stands for progressive denoising, applying open denoiser and RT. RT is the denoiser that is based on open denoiser, but it also considers the variance of the samples. Again, for these crops, the error is lower for our method. And for the entire image, our results are comparable or even better, especially at the higher sample counts, with respect to those produced with PD. Regarding the flip score, again, our method is comparable or better at the higher sample counts. These are two plots that represent the mean square error calculated for all 10 scenes produced with Denisova, that like I showed before. And the graph with the dots represents the following special situation. The situation when the denoising stops at iteration 128. In other words, it means that we continue to blend the Monte Carlo estimates obtained at higher sample counts, but with the denoised result obtained at iteration 128. So you can see that even in this case, the results are better, and which is very important, the sequence of the denoised images converges to the reference. Here are the results of the mean flip score in comparison with the deep learning-based PD. As you can see, our method is slightly worse at the lower sample counts, namely until the sample count 16, but then becomes comparable or even better at the higher sample counts, as you can see on the right. We also applied our method on the recently proposed advanced realistic arrangement technique for biomedical volumes. As expected, also in this case, our algorithm works. Another example. On NVIDIA RTX A4000, the blending algorithm we proposed takes about 32 milliseconds, in which open denoiser takes about 15 milliseconds, Schur calculation about 16 milliseconds, and the curves calculation takes less than 1 millisecond, together with some filtering if needed. Against 33 milliseconds that requires PD algorithm. Similar to deep learning-based methods, our technique is not free from the artifacts, and these crops are extracted from the exact scene of the Mitsuba scenes that I showed before and blended at random sample counts. As you can see on the scenes with a lot of fine details and at higher sample counts, our algorithm works especially well. But at lower sample counts and in the homogeneous zones, we can observe some artifacts. So, we proposed a fully analytical method to blend Monte Carlo estimates with their denoised counterparts. The method can be immediately applied on any denoising algorithm, deep learning based or not, and can blend the images that are obtained at different sample counts. The method can be applied during the progressive denoising or as a final step for the denoising of the non-fully converged Monte Carlo estimate. We saw that actually the results depend a lot on the quality of the denoised images estimation. So some better estimation based on recent works for Schur calculation can be applied. As I told, we applied our method on the pre-generated images obtained at the power of 2 sample counts. But the real-time blending can be very interesting because some interesting consideration about the convergence curves calculation on the fly or stop iteration for the denoising can be get from this application. And finally, our method can be applied on adaptive sampling, as the algorithm already gives you the weights that can guide the adaptive sampling process. Thank you. You can find the source code of the implementation on GitHub.
Thank you, Elena. Very good work, very good presentation. I would like, okay, the third speaker we have here. Yeah, do we have any questions in the audience?
Did you try your technique on more traditional computer graphics scenes?
What do you mean by?
Not medicine related or something.
Yeah, as the question is if I tried the algorithm on the traditional scenes. Yes, initially we tried our method on the Mitsuba generated scenes. Yeah. So the algorithm should be independent on the Monte Carlo path tracing method that you use.
Other questions? I guess I have one. You mentioned that the estimates might not work that well for lower sample counts. Do you have any ideas what would you need to modify in the method to make it work?
Yes, this problem is the result of the normal distribution of the samples. So when we have lower sample counts, the distribution is far from normal. And actually, I think the best solution is to not apply the method on the lower sample counts, makes your denoising algorithm to run, and then start to blend from like some or fixed sample count or some empirically found sample count.
Got it. Thank you. Any other questions? If not, then let's thank Elena again.
Thank you.